Hi, welcome to the statics tutorials. So with this problem, we're going to draw the shear and bending moment diagrams for this beam. So this beam has a smooth frictionless pin at A and a contact with the roller at frictionless roller at B, and then a 3 kilonewton force that acts right in the middle. This beam is 2 meters long. So first we need to draw our free body diagram. So for pin at A, we have an AX and an AY. Here's our applied 3 kilonewton force. And then here's our BY force from our roller. Then we need to solve for those reactions. So we'll do sum of moments about A. We have the 3 kilonewtons times the 1 meter here, which is negative. And then we have BY times the 2 meters here, which is going to be positive, and that'll equal 0. So we get BY is equal to 1.5 kilonewtons. Doing sum of forces in X equals 0. AX is the only term in that equation, so we get AX is equal to 0. And then sum of forces in Y equals 0. We have AY and BY minus the 3 kilonewtons, and so we find that AY is 1.5 kilonewtons. Just in general, when we have a beam that's symmetric around the center, and then the loading is also symmetric around the center, really the loading should be split between the two ends if it's supported just right at the ends. So that makes sense that we have the 3 kilonewtons here, we have 1.5 kilonewtons on this side, and then 1.5 kilonewtons on that side from the reactions. So let's draw our shear and bending moment diagram. So let's start at a shear of 0 and take a look at what we have in the beam. We immediately hit AY. So AY is a positive 1.5 kilonewtons, and so that's going to take us from 0 up to 1.5 kilonewtons. Now we're going to check the beam and look for any distributed load that we have. We don't have any distributed load, so that means we have a 0 slope. So our shear is just going to come on over with a 0 slope until we hit the 3 kilonewtons. When we hit the 3 kilonewtons, we're at 1.5. We're going to subtract off 3 kilonewtons because the 3 kilonewtons is going down. So we'll come down to this negative 1.5 kilonewtons here. And then we check the beam again. We don't have a distributed load over here, and so our slope is going to be 0 because our distributed load is 0. So then we'll come back over here, and then we hit BY. BY was positive 1.5, and so we're able to account for everything and wind up at 0 here. So you can think about it starting from 0 and stopping at 0, or some folks like to think about it as starting from either the force or the net reaction, the reaction or the net force at A over here, and then stopping at the net force or the reaction over here at B. So we're starting at 1.5 here because of AY, and then we're ending at the negative of BY over here. And either way of thinking about it is fine. Let's take a look at the moment. So we can calculate the area in the shear, and it's going to be 1.5 kilonewtons times 1 meter, which gives us 1.5 kilonewton meters. Over here, this area is really the same. It's just going to be negative. So these areas are going to tell us how much our moment changes when we go over the same distance. And then the shear gives us the slope of the curve. So our bending moment's going to start here at 0. We have a positive constant slope of 1.5. And the total change is 1.5 kilonewton meters. So that means it's going to be a straight line increase from here out to 1.5. So there's our straight line increase. Over here we have a negative slope of negative 1.5, and the area is negative 1.5. So we're going to go from our 1.5 here and drop 1.5 and go back to 0. So our slope here is 1.5 kilonewton, and our slope here is 1.5 kilonewtons, but it's negative. If you prefer the algebraic approach, you can create your sections. So this is a section view. We need a section in here. We can really only section when x is 0 to 1 meter. So we've got this section here for the 0 to 1 meter. Let me jot that down. And then we can do our sum of forces in the y direction. So we get that the negative shear plus the 1.5 kilonewtons is equal to 0. So the shear is 1.5 kilonewtons in this region. So it's just exactly what we got over here from the graphical method. And then we'll do a sum of moments about that cut edge and set that equal to 0. And we get that the bending moment minus the 1.5 times our x distance is equal to 0. So our bending moment is equal to 1.5 times x. That's an equation of a line that has a 0 y-intercept and has a slope of positive 1.5 kilonewtons. So you can see we're getting exactly the same result. Now, to finish it off algebraically, we need to section through over here. We can't use the same section here because once we get x past a meter, then we have this 3 kilonewtons acting on it that we haven't shown in our section free body diagram here. So we do another section over here, or you could think about this other section really just being the mirror image of this section just on that side. But either way, you'll get exactly the same result. You'll get the constant negative 1.5 for the shear, and then you'll get this negative 1.5 slope for the bending moment. Thanks for watching.